Hey there, awesome physics students. Let's talk about a velocity selector. In a previous video, we talked about how mass spectrometers work. And if you recall, what we needed to do was ionize carbon atoms and then send them all into the mass spectrometer with the same velocity. So how do you ensure that that velocity is the same every time? That's what a velocity selector does. And even though modern mass spectrometers do not necessarily need a velocity selector, the velocity selector demonstrates important differences between the magnetic and the electric fields and how those influence the motion of the charges. So let's get started. Let's imagine that we have a positive charge and we're going to send it into the velocity selector with a velocity v. Okay, we're just going to use positive charges to start with because they are fairly simple to understand. We don't have to get confused on the directions. And we're going to put our magnetic field in this way, perpendicular to the screen, so that points into the screen this way. All right, so as the charged particle comes in here, the velocity vector points this way, qv points this way as well, and so if you take your fingers of your right hand, point them along qv, push them into b points into the screen, your force is going to point up, and these are going to curve upwards into an arc and strike the top of the screen here. Okay, so the important idea here is that the magnetic force, as this is coming in here, is going to point up. Okay, the strength of the magnetic force, because it depends on QV cross B, V and B are perpendicular, so the magnitude of this is just going to be QVB. There's a sine theta on here as well. That's the sine of the angle between V and B. But again, I mentioned that V and B are perpendicular, so that angle is 90 degrees. QVB sine 90 is 1, so I'm going to leave that off. Okay, so in this scenario, though, the force will be up. All of these will curve upwards and strike the top of this, this velocity selector here. The next step, to prevent that, what you do is you put an electric force on it. And to put an electric force down on it, you create a uniform electric field that points down. And that's going to create, this is a positive charge. The positive charge feels a force in the direction of the electric field. And so that electric force is going to point down. The magnitude of that electric force is going to be the amount of charge, Q, that's positive here, times the magnitude of the electric field. Now this is an important point. We have the magnetic force and the electric force pointing in different directions. And this illustrates an important feature of magnetic forces versus electric forces. Electric forces point in the direction of the electric field. Magnetic forces, on the other hand, point perpendicular to the magnetic field. So that's a little bit more confusing and a little bit more complex. The other important point is that the magnetic forces depend on the velocity of the charge itself, whereas the electric force does not. They both, however, depend on this charge Q. So if I sum the forces in the vertical direction, I'm going to get QVB up, and then I'm going to get QE down. And the goal here with the velocity selector is to have them come straight through with no acceleration. So I'm going to have set that the net force equal to 0. And you'll notice that the Q's are going to cancel. We can divide both sides by the Q's. And that's going to give us VB is equal to the electric field. Or in other words, the velocity is going to be the electric field divided by the magnetic field. So the idea here with the velocity selector is that I have knobs that can control the electric field and the magnetic field strengths, and I can tune those exactly right until I get the exact velocity that I want. So if they're coming in too fast, the magnetic force will be big, and they're going to curve upwards and strike the top here and not make it through. If they're coming in too slow, the magnetic force will be too weak, and the electric force will win, and they'll curve downwards and strike the bottom. It's only the ones that have just the right velocity. The velocity that is equal to the electric field over the magnetic field, those will come through unscathed and won't curve at all. They will have zero net force, and those are the ones that we're selecting. Okay? Hopefully this helps you understand how the interaction between electric and magnetic fields and forces on charges.